So, as you may remember from 201, part of the power of the potential energy concept is that if you know the change in the potential energy, then you can find the change in the kinetic energy, assuming that only kinetic and potential energies are involved in a process. So, let's say we have a roller coaster and it moves down a track, then as it drops, its potential energy decreases by mgh, and its kinetic energy will increase by 1/2 mv squared. In that case, the masses cancel out, so you find that g times h is equal to 1/2 the velocity squared. So if you know by how much the kinetic energy is increased, and you can solve for the final velocity as long as you know the distance that the object has dropped, or the roller coaster has dropped. In the case of a uniform electric field, the potential energy changes as QED, where Q is the charge in coulombs, E is the electric field strength, and D is the displacement in the direction of the electric field. So, if the charge is positive and the displacement is in the direction of the electric field, the kinetic energy will increase, right? It's like it's rolling down a hill. And the increase in kinetic energy is equal to 1/2 the mass of the object times the final velocity squared minus the initial velocity squared. So in most of our problems, we'll start from rest, so this is pretty straightforward, but occasionally we might have an initial velocity. Notice mass and charge do not cancel each other out here, so often we will ask you to find the velocity of an electron, a proton, or an alpha particle. So in those cases, we give you those masses in our formula sheet, and so an alpha particle, you'll remember, is 2 neutrons and 2 protons, so the mass is pretty close to 4 times the mass of a proton. So the point is, if we know the change in the electric potential energy, then we know the change in kinetic energy, and then if we know the mass, we can find the velocity. Okay, so now we're given a problem. We have an electric field with a strength of 3,000 newtons per coulomb pointing to the right, and we've placed a proton at point A. The proton moves from point A to point B to the right, which is in the direction of the electric field, and the distance here is 5 centimeters. So, and then we are asked by how much work is done by the electric field. Well, the work is the charge times the electric field times the displacement. The positive proton is moved in the direction of the electric field, so the positive work is done by the field. The magnitude is QED, which is 1.6 times 10 to the minus 19 coulombs, which is the charge of the proton, times 3,000 newtons per coulomb, the field strength, times the displacement, which is 0.05 meters. Notice we need to convert centimeters to meters to get the proper units of Newton meters or joules for our energy. So that gets us that the work done is 2.4 times 10 to the minus 17 joules. So now we continue with this problem. Instead of being asked the work done, what if we were asked the change in velocity if the proton started at rest? Well, we just found the work done, so that means the change in the kinetic energy is equal to the work done by the electric field. Since the electric field is the only thing that is causing work to be done, or the only thing that's causing the force to act on our proton, so that means our initial kinetic energy is 0 because the proton is starting at rest, and that means that the final kinetic energy is the work done, which is again 2.4 times 10 to the minus 17 joules. So, last we want the speed. Well, the kinetic energy is equal to 1/2 mv squared, and we know the kinetic energy, so all we need now is the mass of a proton. The mass of a proton we find to be 1.67 times 10 to the minus 27 kilograms, so we plug into our kinetic energy equation and solve for V. So we get that the kinetic energy times 2 divided by the mass of the proton, and then we take the square root of that to get that the velocity is 1.7 times 10 to the 5th meters per second. So the proton here is moving pretty quickly after accelerating for only 5 centimeters. All right, so I guess it's your turn now to do a problem relatively similar to this one. I think we will stop here today, so good luck with the rest of your classwork, and take care of yourselves.